Okay, so now let us proceed with the properties of the definite integral and the first fundamental theorem of calculus. So in this part, we need to remember the following properties for your definite integral. Um, for this part, as you can see, there are similar counterparts for the derivatives. So for example, this one, you can move the constant outside of your integral and solve for the integral first and then multiply by c. Here we have the integral of the sum or difference is equal to the sum or difference of the integrals. Next, we have here the integral of f from a to a. So from a point to itself is always equal to 0 since the area that will be formed under the curve is non-existent. So it's just a line here and the area of this one is 0. Next, for this part, the integral of c from a to b is just the area between the area that is formed by the curve y equals c and then on the interval a to b. So if you have here a straight line C, what we have is a rectangle. So the area would be base times height. And so we can interpret this one as the integral of dx from a to b and then multiply by c. So that will be the integral of c times b minus a. Next, if you have the integral of f from b to a, you can flip the limits of integration. So we have from a to b and then add the negative sign. So the integral of f from b to a is equal to the integral of a, uh, no, the negative of the integral of f from a to b. And then finally, we can split some interval. So if you have an interval p and q, a p to q, you can insert a point r so that you have the integral of f from p to r plus the integral of f from r to q, regardless of the orders of p, q, and r on your interval AB. Next, we have the fundamental theorems of calculus. So you need to remember the properties of definite integral because we will be applying it to solve some problems relating to the fundamental theorem of calculus. Now, the first fundamental theorem of calculus states that if f is a function continuous under closed interval AB and x is any number in AB, then capital F is defined if capital F is defined as your antiderivative of f from a to x, then the derivative of f is equal to f of x. So what does this tell you? So for this theorem, what we do is the derivative of your integral, since they are inverse operations. So as you can remember, the derivatives, the reverse operation is antiderivatives. So if you are applying the derivative of f, so you are basically looking at the derivative of the integral of f. So this one becomes f prime and um, in a simplified sense, these two operations, the derivative of the integral cancels out. And so you have f of x. This note that this explanation is not really true for there are some properties that we need to apply. But basically the idea is just f prime is equal to what is inside the integral. Okay. So how to find h prime given that h of x is from a point A to g of x f of t dt. So these are some type of questions that usually pop up in the exam. And to solve this, we apply the following steps. So if the integrand, if the integral is not of this form, so meaning the lower limit of the integration is not a constant and the numerator is a function, is not a function, then we need to apply some properties of definite integrals. usually you'll be given this integral wherein the bottom limit of integration and upper limit of integration are both functions. So what we do is to split them up to choose, first choose a point that is inside the domain of your function. So choose point in domain of your function. So for sine of t, the safest choice would be 0 since it is also sine is continuous everywhere, so any point will do. But I just chose 0. For most of the cases, usually I use 0 for this part. So if we split this interval from x to 2x, I'll now have the integral from x to 0 plus the integral of from 0 to 2x. After that, since the first integral is flipped, so meaning the limits below is a function and then the limit above is a constant, we need to flip it. So applying the properties of definite integral, so I now have negative of the integral from 0 to x of sine of t dt and then plus 0 integral from 0 to 2x of sine of t dt. And then finally, we apply this formula, h prime is equal to f of g times g prime, which is basically your chain rule, right? So we need to find g prime for each of these functions. So for the first function, the first integral, we have the negative of integral of 0 to x sine of t dt. So to solve for this, the derivative of this integral would be sine, and then t will be replaced with x, and then multiplied by the derivative of x, which is 1. And then don't forget the negative sign from the um, process where even we flip the integrals, the limits of integration. And then next, for the integral from 0 to 2x sine of t dt, we have sine of 2x. So sine, and then yung t replaced with 2x, and then multiplied by the derivative of your 2x, which is equal to 2. And thus, we have h prime is the sum of these two. So negative sine of x plus 2 sine of 2x. Now, going to the exercises that we have. For number 1, find f prime if f of x is equal to negative the integral of the square root of t squared plus 1 dt from negative 3 to tangent inverse of 2x. Notice that for this integral, we already have the form that we want since the the lower limit of integration is negative 3 and the upper limit of integration here is a function. So we just need to find the derivative of your g of x. So that is 1 over 1 plus u squared times the derivative of u. So that is 2x times 2. So you have 2 over 4x squared plus 1. And applying the formula that we have for the first fundamental theorem of calculus for f prime, we have f prime of x equals f of g of x times g prime of x. So t will be replaced by g of x. So that is tangent inverse 2x raised to 2 and then plus 1 multiplied by the derivative of g, which is 2 over 4x squared plus 1.